Today we are going to learn about mastering convolutional layers in TensorFlow. We will explore how to effectively implement and optimize convolutional layers for handling image data, enhancing model performance, and debugging common issues. Welcome to our video on mastering convolutional layers in TensorFlow. In this session, we'll embark on a journey to understand convolutional layers, a fundamental component in deep learning models, especially when dealing with image data. Convolutional layers help in extracting features such as edges, textures, and patterns, which are crucial for tasks like image classification and object detection. By the end of this video, you'll have the skills to implement and optimize these layers in your TensorFlow models to enhance performance and accuracy. Let's dive in.
Convolutional layers are adept at handling the spatial and temporal dependencies in an image through the application of relevant filters. By scanning over the image, these layers help in capturing the spatial hierarchies that are present. This is particularly beneficial as images typically consist of multiple layers of pixel data, making it crucial to analyze them in a structured manner. Unlike fully connected layers, convolutional layers significantly reduce the computational cost by sharing weights across different regions of the input image. This makes them highly efficient. Moreover, convolutional layers are invariant to transformations such as translation, scaling, and rotation, making them robust for various image processing tasks. These properties make them indispensable for applications like image classification, facial recognition, and more. Understanding these benefits allows us to leverage convolutional layers effectively in our deep learning models. Setting up a convolutional layer in TensorFlow is a straightforward process, thanks to the powerful Keras API. To begin, you'll need to import the necessary TensorFlow libraries and ensure your environment is correctly set up. The primary class you'll interact with is tf.keras.layers.conv2d, which allows you to define a 2D convolutional layer. When creating a convolutional layer, you need to specify the number of filters, the kernel size, and the input shape. The filters determine how many feature maps are produced, while the kernel size defines the dimensions of the filter matrix that will be convolved with the input. You'll also need to consider parameters like strides, padding, and activation functions, which we'll explore in more detail in upcoming sections. By mastering these configurations, you can effectively harness the power of convolutional layers in your TensorFlow models. Choosing the right filter size and stride is crucial for optimizing the performance of convolutional layers. The filter size determines the receptive field of the layer, which affects how much detail the layer can capture. Common filter sizes include 3x3, 5x5, and 7x7, each offering a balance between capturing fine details and reducing computational complexity. Strides, on the other hand, control the step size of the filter as it moves across the input image. A stride of 1 means the filter moves 1 pixel at a time, while a stride of 2 means it skips every other pixel. Larger strides can reduce the spatial dimensions of the output, leading to faster computation, but may also result in loss of detail. It's important to experiment with different filter sizes and strides to find the optimal configuration for your specific use case. Remember, the goal is to capture relevant features while maintaining computational efficiency. Padding is a key concept in convolutional layers that affects how the filters interact with the input data. There are 2 primary types of padding, same and valid. Same padding adds zero-valued pixels around the input image, ensuring that the output dimensions are the same as the input dimensions. This is particularly useful when you want to preserve the spatial dimensions of the input throughout the network. Valid padding, on the other hand, means no padding is added, resulting in smaller output dimensions. This can be beneficial for reducing the size of the data as it flows through the network. The choice between same and valid padding depends on the specific requirements of your model and the nature of the data you're working with. Understanding the impact of padding on output dimensions is crucial for effectively designing and optimizing convolutional layers.
Activation functions play a vital role in convolutional layers by introducing nonlinearity into the model. This nonlinearity allows the model to learn complex patterns and representations from the input data. The most commonly used activation function in convolutional layers is the rectified linear unit, ReLU, which has become popular due to its simplicity and effectiveness in overcoming the vanishing gradient problem. ReLU activates only positive inputs, while negative inputs are set to 0, providing a sparse representation that can enhance model performance. Other activation functions include sigmoid and tanh, which can be used in specific scenarios where their properties are advantageous. Choosing the right activation function is crucial for ensuring that your model is capable of learning and generalizing well from the data.
Convolutional layers are a cornerstone of many practical applications in the field of computer vision. One of the most common uses is in image classification, where convolutional layers help identify and categorize objects within images. In facial recognition systems, these layers are used to extract facial features and match them against known profiles. Object detection applications leverage convolutional layers to identify and localize objects within complex scenes, enabling tasks such as autonomous driving and surveillance. Semantic segmentation is another area where convolutional layers excel, allowing for pixel-wise classification that is invaluable in medical imaging and geospatial analysis. By examining real-world case studies, you can gain a deeper understanding of how convolutional layers are implemented in various domains and the impact they have on advancing technology.
Debugging convolutional layers can be challenging, especially when dealing with complex models and large datasets. One common issue is convergence, where the model fails to reach an optimal state during training. This can often be addressed by adjusting the learning rate or using optimization techniques like ADAM or RM-sprop. Vanishing gradients are another frequent problem, particularly in deep networks, where the gradients become too small to effectively update the weights. Implementing activation functions like ReLU can help mitigate this issue. Overfitting, where the model performs well on training data but poorly on unseen data, can be addressed by using techniques such as dropout and data augmentation. Visualization tools like TensorBoard can be invaluable for gaining insights into your model's performance and identifying areas for improvement. By understanding and applying these debugging tips, you can enhance the reliability and accuracy of your convolutional layers. As we conclude this video on mastering convolutional layers in TensorFlow, let's recap what we've covered. We've explored the importance of convolutional layers in image processing, the process of setting them up in TensorFlow, and the crucial parameters involved like filter sizes, strides, and padding. We've also discussed the practical applications of these layers and provided tips for debugging common issues. Remember, mastering convolutional layers requires practice and experimentation. By applying the knowledge gained in real-world scenarios, you can optimize your models for better performance and accuracy. Thank you for joining us, and we encourage you to continue exploring the potential of convolutional layers in your deep learning journey.